All right. Well, it's 8:30 in California, so let's get going here. Welcome everybody to the inaugural meeting of SEPM's new Planetary Sedimentary Geology Research Group, maybe the Planetary Research Group for shorthand. Yeah, thanks for being here. So please, if you can find the Q&A or the chat portion of your control panel here in GoToWebinar, please feel free to introduce yourself there. Now, this doesn't quite work like a Zoom chat where we can all see everything, but the information will come to the organizers and we will send it out later. So, if you want, feel free to share your name, your current position, maybe you're an undergrad and where you are. What you're currently seeking. So for instance, maybe you're an undergrad looking for a grad school advisor, maybe you're a faculty member somewhere looking for a postdoc, feel free to share that. And of course, some contact info where somebody could get in touch with you. And again, we will share this information after the conference here. Okay, so my introduction, I'm Ben Cardenas. I'm a postdoc at Caltech, and I will very briefly be guiding us along with help from Cassie Turley at SEPM through just a few introductory slides here to get some points of business out of the way. So first, the code of conduct, SEPM's code of conduct. The society, capital S, takes any form of harassment seriously, and there may be significant consequences for any unacceptable behavior, including but not limited to membership revocation, prohibition from future society activities, and notification to other concerned parties. You can find the code of conduct and some other information at this URL here. Maybe Cassie can drop that into the chat as well, a link. Okay, so who is this community, the Planetary Research Group? It's brand new. It started coming together last year in 2020. The vision here is to help bring together sedimentary geoscientists who are working on modern sedimentary processes and the ancient sedimentary records of planets and moons, including Earth. And in particular, I think this is something unique we get with SEPM, which is traditionally, an Earth-based sedimentary geology society here. By housing this research group in SEPM, we really get a nice opportunity to bring together these Earth folks with these planetary folks, hopefully, with the end goal here of making some nice new innovative work following from some great discussions like the one we'll have today, I think. So why join the group? Networking opportunities, of course, especially once we start meeting in person. And we do plan to have in-person as well as virtual meetings, although we'll get into that a little bit later here. There will be an email listserv. We're still working on this. Now, as a member of SEPM, you also get the benefits and the journal access, all the other things that come along with being a part of that larger community. But you don't need to be an SEPM member to be a member of the research group. And again, ultimately the goal here is that this group becomes a channel for collaboration and the sharing of resources and opportunities. We've got a few upcoming events in the broader SEPM community, including an SEPM editors Q&A live webinar, which ought to be pretty interesting, and the AAPG annual convention, which SEPM will also have a presence at. Okay, so before we move forward on to Katie's talk, which we're all here for, we have a few poll questions we'd like to ask you. Which Cassie will pull up now. Now, Cassie, I don't know if you've pulled up the poll questions, but I cannot see them. So if you have, you may need to read them. Okay, maybe I can do that. Okay, so our first poll question, are you a current SEPM member? All right, I see furious clicking. Okay. Okay, now which best describes you? Are you an undergrad, a postdoc, early or late career, retired? All right, we're at 94% voted. Oh, 96. Excellent. Okay, question 3 out of 5. How did you hear about this virtual meeting? All right, y'all are quick. 91%. Oh, 99%. Nice. Okay, question 4 out of 5. Now this one is a little longer. What is your preferred research group meeting frequency? Got a few options here, so take your time. All right, 80% voted. All right. Okay, final question. Which aspect of the Planetary research group are you most interested in? This might be meetings and networking, the email listserv once we get that going. There's also the possibility of an SEPM special publication. All right, 96%. Okay, wonderful. That's it. Thank you all very much. We'll share those results with you very soon. Okay, so the next steps here, If you're interested in being involved in the future, please send me an email at bencard@caltech.edu. Now, a lot of you have already reached out. Don't worry, we will definitely be in touch, especially once we're looking to organize potentially some in-person meetings, okay? So thanks for reaching out if you have already. Okay, today for our talk, I'm very happy to introduce Katie Stack Morgan. Katie received her PhD from Caltech in 2015, and she's currently a research scientist at JPL here in Pasadena. Now, she wears many hats at JPL, including that of Deputy Project Scientist of the Perseverance Rover mission, and she is also a participating scientist on the Curiosity science team as well. So I'm going to hand over control to Katie here, and I look forward to hearing her talk. I'm sure All right, Katie, I think you're in control now.
Okay, thanks, Ben. Can you confirm that you can see my screen? And I'm about to go into presentation mode. So let me know if you are seeing it the way that it should be.
Looks great.
Okay, great, thank you. And apologies for not being able to show my webcam. I seem to be caught in an infinite loop here in security preferences. So apologies for that. Thanks everyone for calling in to hear my talk, and thank you very much, Ben, for the invitation to speak at this inaugural meeting. I'm excited to be here. And so I was asked to give an update on the Mars 2020 Perseverance rover and its first results. So I'll be talking through that. I'm guessing many of you are familiar with this mission, but I'll go through some of the background and introduction to the mission and what it's all about. And then I'll get into some of the geologic context for the landing site, and then talk about some of our early results with a focus on some of the really exciting sedimentology observations that we have been making thus far since we landed on the surface back in February. So with that, I'll get started here. All right, so Mars today is very different than the Mars that we think might have existed in the past. Mars today is a pretty barren, cold, dry place. But we have evidence, abundant evidence at this point from both rover and orbiter observations, suggesting that Mars was indeed very different in the past and perhaps more Earth-like. And we think sometime around 3.5 to 4 and beyond billion years ago, Mars might have been more Earth-like. And that's really exciting in the chance to study the early solar system in a period of time when life was emergent here on Earth. And so there is exciting potential here to explore another planet, and one that's taken a very different path in terms of its habitability, beginning as a habitable planet and turning into one where life is really not supported at the surface. And so because of the potential for answering these exciting questions about Mars, NASA has been pursuing a Mars exploration program, and this will be very familiar. Its goals are to determine if life ever rose on Mars, what the climate of ancient Mars was like, what's the geology, what are the processes that dominate the surface and interior of Mars, and then with an eye towards future human exploration. And so there are some common themes that weave in between and throughout these main goals, and these are things familiar to many. Follow the water, that was the goal of many of the early Mars surface missions, like the Spirit and Opportunity rover. Then we tackled the search for habitability and habitable zones, and that was really the focus of the Curiosity rover that's been successfully exploring a place called Gale Crater since 2012. And then we have this search for signs of life, and that's really where the Mars 2020 mission and the Perseverance rover fits into the Mars exploration program goals. And so bringing back this question of, okay, seeking signs of ancient life, the oldest accepted evidence for life on Earth is found in about 3.5 billion year old rocks. And we know that life probably emerged earlier than the specific record that we have. And so this is a period of time that's actually not particularly well recorded in the rock record here on Earth. Really, really ancient rocks are indeed found throughout the Earth's surface, but they're relatively rare. In contrast, about 50% of Mars's surface is older than 3.6 billion years old. So this gives us an opportunity in studying Mars to study a period of time, again, not well recorded in Earth's rock record, and exploring the period of time when life was emergent on Earth and possibly on other planets as well, with Mars being, I think, one of the best candidates for that. So that really is one of the main motivations for why we look to Mars and ancient Mars to help answer this question of whether there was life elsewhere in the solar system and what the circumstances surrounding its emergence might have been like. And so despite the fact that we have sent numerous missions to Mars, both surface and orbiter and lander, this question of whether life once existed on Mars still remains. While we have been very successful in identifying those habitable environments on Mars, we have not yet confirmed the presence of ancient life on Mars. And so that remains an outstanding question. What were the prebiotic conditions that existed on Mars and that might have existed on early Earth as well that could have led to the emergence of life? So that's a big outstanding question that we have. Also unresolved for Mars is the timescale, the geologic timescale that we have. We have for Mars a relative timescale, and that much of that is based on crater chronology developed based on lunar samples and crater counts on the moon. And we've extrapolated that for use on Mars, but generally speaking, things are very much in a relative sense. And so there's this question, when did the important geologic events happen on Mars, and how are they related to other things that occurred on Mars, like the potential for life and the presence of water at the surface? So there are big questions about geologic process and timing on Mars that we have yet to resolve, because we have yet to do in situ or absolute age dating for Martian rocks, besides what we get or are able to do from meteorites, which lack some of that geologic context to really help us pin in time some of the major events that have happened in Mars history. Also, I think we kind of unresolved yet for Mars is understanding Mars as a system. And we've made great strides in understanding elemental reservoirs on Earth in the past 50 to 75 years. But on Mars, there are big questions about what was the carbon cycle like, and what about oxygen and sulfur, and so those are outstanding questions that we've made some progress on. But I think the prevailing opinion in the planetary community is that we really need to bring samples with well-documented context back to Earth in order to make progress in some of these really big major areas. And again, with the potential for Mars to have hosted ancient life, these become particularly important questions, particularly in the context area. And so it's in this context that NASA planned and developed and designed its latest flagship mission, which is Mars 2020. And Mars 2020 as part of a notional 3-mission Mars sample return campaign. So here we have the Perseverance rover with that big bold yellow arrow. But the idea is that this mission is part of a multi-mission campaign involving a surface lander, a small rover that we call a fetch rover to pick up those samples that Perseverance collects, and then an orbiter to help get those samples back to Earth. And this is the kind of mission architecture. It's still very much in work. Conversations still ongoing with international partners. But this is the kind of thing that, in the next decade, we really hope and expect to see come together. So that's a very exciting thing. And Perseverance is really the first step in this multi-mission campaign. And so with that in mind, I'll just briefly go over the 4 main objectives of the Perseverance mission. So as for previous rovers, Perseverance has the goal of characterizing the geology of the landing site. Getting really at that seeking signs of ancient life objective, we have an astrobiology objective to characterize the astrobiological potential of the landing site and seek signs of ancient life in the rock record. And previous missions have had this as a goal as well, but I think Mars 2020 and Perseverance really take it to the next level and say, because we are part of Mars sample return, it really truly is our responsibility to find those samples and collect them and document them that may have potential for signs of ancient life. And so that feeds into our sample caching objective, which is to put together a returnable, scientifically compelling cache of samples to support future analysis of these samples back on Earth. And of course, preparing for humans, that's a common goal that Mars missions have as we take small steps towards preparing for humans. And so Perseverance has, along with it, a couple of technology demonstrations that work towards this particular goal. So I'll talk just a little bit about the instrument payload, the science instrument payload for the Perseverance rover. And so we'll shortly go through some images from some of these cameras in particular. And so this is a payload contributed by the US and also international partners. We have a number of cameras. I mean, this rover has the most cameras of any rover or mission that we've sent to Mars. The main science cameras are the MASCAM-Z instrument suite, which are these two cameras here on the mast or the head of the rover. And this is they're zoomable, so this is an improvement on similar cameras that rode along with the Curiosity rover. On the turret or the arm of the rover, we also have a camera there. It's called a Watson, and that rides along with the Sherlock instrument suite, and that's very similar to the Mars hand lens imager that's on Curiosity. And so that allows us to see textures at the kind of micrometer scale up close and very personal with the Martian surface. We also have an imager on SuperCam, and I'll show you some really fantastic images from the remote micro imager that we have on this instrument. And so we also have mineralogy and geochemistry instruments and instruments that can detect organic matter. And so SuperCam and Sherlock have Raman spectrometers within them, and they can analyze the organic content of the mineralogy of the surface. And Pixel is our X-ray spectrometer to look at elemental chemistry, and that's something that SuperCam with LIBS capability does as well. We are bringing to Mars the first ground penetrating radar, and that's with the RIMFAX instrument suite here on the back of the rover, so we can see subsurface structure. And then riding along as part of that future human exploration goal are the META and MOXIE instruments. META is a weather package that is built on heritage from Curiosity's REMS suite, and MOXIE is a technology demonstration to produce oxygen from Martian CO2 with an eye towards helping to support future human exploration and human return to Earth from Mars in the future. And so that's our payload. And so I'll show this slide. This is one we often show to really kind of hit home the value of our instrument suite for accomplishing our objective of seeking signs of ancient life. So we, of course, have the ability to core and cache. And so here's an example of a rock core that Perseverance can collect. And our plan is to collect, we have about 43 tubes, and we plan to collect about 30 science samples during the lifetime of the mission. But to enable that selection, we have our instruments on the arm, and so that's Pixel and Sherlock, and they really bring, I think, Mars in situ science, rover science to the next level, where previous instruments have been able to identify elemental geochemistry or the presence of minerals, but now with Pixel and Sherlock, which are mapping instruments, we can actually map the spatial distribution of elements, minerals, and the distribution of organics within rocks, which when coupled with the high resolution imagers really help us build a case using all of those lines of evidence that what we may be seeing could be a possible biosignature. And these are really exciting capabilities that allow us to do, I think, petrology on the surface of Mars in a way that we haven't been able to do with previous rovers. So that's some of the things that make this payload particularly exciting. Some of you may know that we carry along with us a helicopter. This is another technology demonstration. I won't talk much about the helicopter for the remainder of the talk, but I'll just put this out here. We can enjoy the beauty and wonder that is flying a helicopter on the surface of Mars, and then we'll move back to the geology of the mission. But it's just kind of blows my mind to see us accomplish something like this, and it's been exciting to follow along with this helicopter, which is called Ingenuity, its flights on the surface of Mars, and its continuing exploration and acquisition of images that may help us with our science mission. All right, so I'll talk a little bit about Jezero crater, which is the landing site for Perseverance. And so this site was selected because of these fantastically preserved ancient lake and delta deposits, and we can just see those here in this image. This white circle here was the landing ellipse for Perseverance. And so that delta is here, and we'll zoom in on that. And the diversity of habitable environments that we thought were preserved in the rocks in this crater. So of course the delta was a prime target of that, and I'll go through some of the other rock units within this landing site that have piqued our interest from an astrobiology perspective. And also the fact that this crater is in a region of Mars containing some of the oldest rocks that we have on the planet. So between 3.5 to 4 billion years old. So giving us an opportunity to really see and capture this interval of time when perhaps life emerged on Mars and where big planet-wide global changes were happening in terms of the habitability of the planet. So by collecting samples throughout this time window, I think we have the ability to really reconstruct an important part of solar system and Mars history. Okay, so Jezero is also, and so I mentioned some of the context here, but Jezero is perched on the inner rim of the Isidis impact basin, which is one of several major, pretty massive impact basins on Mars that has been age dated to about 3.9 billion years. And another thing that makes Jezero crater, I think, appealing from a contextual perspective for sample return is the fact that it's relatively well constrained, as best we can know it with our relative way of determining age on Mars, between the Isidis impact event and then Syrtis Major, which was a major volcanic center that has been kind of relative age dated to about 3.5 to 3 billion years. So based on our understanding of these two major events, things happening in Jezero are kind of bookended by these two major events on Mars with global implications. Okay, so I'll do a really quick step through some of the major units, and then we'll actually take a look at what these units are looking like now that we're on the ground. So most of Jezero is, the interior of Jezero is covered by this mafic crater floor. And over here on the left, I have kind of our running sample tally, which is something that we have thought about strategically, both before we landed and now very much so that we're on the surface. You know, what our sample cache might look like as we go and explore Jezero. So this mafic crater floor is one of the first targets. The fact that it's heavily cratered was exciting for the potential to calibrate crater chronology on Mars. You know, there are a lot of challenges there. So we'll see what our ability to do that is. But there have been different ideas about what this unit is, and perhaps a volcanic origin, which again would really contribute to those absolute age dating goals of Mars sample return. Then we have a very interesting basin filling unit here that is most distinctive in its mineralogy. We see from orbit that is olivine and carbonate bearing. And the carbonate part of this is what I think really gets folks excited, because carbonates are relatively rare on Mars, and Jezero happens to be one of those places where we have made detections of carbonate using orbital spectroscopy data. And so the opportunity to understand more about the carbon cycle on Mars and also the astrobiological implications of the presence of carbonates in an ancient lake basin is certainly very tantalizing. And so this is a unit that may also correlate with similar rocks outside the crater that cover this region. So there have been different ideas about what this unit is, and we're excited to explore, and I'll show you some of the first images that we've gotten of this unit on the ground. Then, of course, we have the Western Delta in Jezero. It was beautifully preserved delta containing clay minerals, carbonate minerals, and representing a really a sedimentologist wonderland in terms of both the orbital data that we have for it and the kind of section that we expect to be able to explore with the rover in understanding what water was doing in this particular crater and what that might tell us about the history of water on Mars. And then finally, we have the marginal deposits, and these are distinct also in the fact that they are carbonate bearing, and they are located on the inner margin of what we think was an ancient lake basin. So this is where we get excited about the potential for these shallow lacustrine environments that might be particularly good at preserving ancient biosignatures if they were present. So this is one of the main astrobiology targets that we have for the mission. Though is a little further off in our strategic plan, given its distance from the landing ellipse and landing location. Okay, and then I'll just mention here the crater wall. This, of course, is not an image from Mars, but we see megabreccia in the crater wall of Jezero. And so we have the potential, once the rover gets up here, to explore crust that is even older than Jezero, and also potentially even older than the Isidis impact as well. So we're getting way, way back into the most ancient rocks on Mars. And so that's also something off in our future to study and thinking about what potential habitable environments might exist in a crater wall setting, as well as the potential to learn about the earliest rocks on Mars. Okay, so now getting to the part where we talk about what it's been like on the surface for Perseverance and some of the data. So here was an image taken by the HiRISE camera on board the Mars Reconnaissance Orbiter, and just a truly fantastic image where we have the HiRISE camera actually capturing Perseverance during its descent to the surface. And there you can see the parachute deployed, and there is Perseverance as that bright dot there on the screen. So this is one of those kind of, everything has to go right to capture an image like this, and the timing has to be pretty perfect. And so this was a pretty fantastic image, and there we have verification that we are on our way to Jezero crater. So eventually we did land, and we landed at this location shown by the star. And we've named it Octavia E. Butler Landing after the visionary science fiction writer Octavia E. Butler. And this is where we begin our mission. I think we were a little surprised when we ended up landing here. This was certainly within the landing ellipse, but a lot of the predicted landing locations were along the delta front. And a lot of our strategic work that we'd done anticipating what the mission would look like assumed that we landed in this area closer to the delta. So once we landed here, I think that, as often happens, it was like, oh, wow, we didn't really think about this scenario. So it's been really exciting with the science team to think about, okay, what does the mission look like now that we have our landing site, and that it's a scenario that we hadn't necessarily expected to plan for. So, but it gives us great access to, in particular, the rocks of the crater floor. So we landed on this heavily cratered Mafic crater floor unit. And just at the edge of the olivine and potentially carbonate-bearing rocks exposed in this outcrop just to the west. And so, as I'll show in a bit, this area will really be the focus of the first year of Perseverance's exploration on Mars. Okay, so this is our landing, but with as a team, we constructed a geologic map using orbiter data, and so we're right here on this, what appears to be a very important contact between the Mafic crater floor and these olivine carbonate-bearing units. It's not super important what these abbreviations are, but it's the crater floor and then this olivine, possibly carbonate-bearing unit. Okay, so here's one more high-res image before we get to the rover data. And I just show this because it's another just really awesome orbiter image where we actually high-res captured the rover upon landing, where we can see very clearly the butterfly pattern left behind by the thrusters as it cleared the dust away from the surface. And so here we are at the Octavia E. Butler landing site. Okay, so when we landed, we took our first panorama, and it looked something like this, which I think is what many of us expect Mars to look like, a barren landscape with a lot of rocks and sand and dust. And so the next slide, we'll zoom in on this boxed area here as kind of one of our first targets that we looked at with some of the instruments on the rover. And so this was a target that we have called Maz, and we're using for the time being Navajo terms. We have a partnership with members of Navajo Nation, and they're providing us with target names. And so this was Maz. This was the first rock that we did SuperCam on, and it is indeed a Mafic rock. But I show this image because it shows the kind of range of interesting textures that we've seen in rocks thus far. We have a lot of these flagstones. We've been calling them pavers, but we also have some interesting textures in the rocks as well. These were the holy rocks that we saw very early on, and so pondered, what's going on here, and what's the difference between these two types of rocks? Is this holiness that we see, is that something inherent to the rock and something like vesicles or dissolution, or is this something? Is this just a wind abrasion phenomenon with these rocks sitting on the surface of Mars for billions of years with the wind acting on it? Is that something that would just happen by wind action? So that's one of the kinds of questions we've been asking ourselves since the start of the mission. Speaking of the holy rocks, I wanted to show this one. This is one of my favorite of the holy rocks. This was the Hedgehog target, and so we got a chance to see the holes up a little closer. And I'll just point your attention over here to the pits left behind by the SuperCam LIBS instrument. We analyzed this rock with SuperCam. But one of the most intriguing things about this rock were these kind of purplish splotches that we noticed, or patches here, that have generated a lot of discussion on the team thus far about whether are we seeing some kind of coating or alteration rind. And so thinking about what that might mean, and seeing these very interesting textures. But as I mentioned, most of the rocks that we see and have seen thus far look like this, quite dusty, and these low-lying pavers. And of course, where they are darker and more gray, that's where there's less dust. But we've really been racking our brains and staring at these images, trying to understand exactly what the lithology of these rocks is. And that's still a topic of debate amongst the team. But I think in recent weeks, we have been moving towards, I think, a consensus opinion that they may be sedimentary in origin, but we're of course still considering whether they could be volcanic or volcaniclastic. But I think as we get our eyes calibrated, and the Curiosity team went through a similar phase as well early on in the mission, where we were trying to figure out, okay, are we looking at volcanic or sedimentary rocks? And so I think as you see more rocks on the surface, you become more confident in your interpretation. And so that's something that we are thinking about very much now for these rocks of the crater floor. This is a GIF, hopefully you can see. So those pavers, often dusty, not a lot of surface texture you can see other than the roughness. But this was one of our first close-up Watson images that we took. And I'll go to the next slide to kind of freeze it on that closest approach. And so you saw previously in the Hedgehog target, those kind of purple splotches at the scale of the holiness of the rock. But we saw also when we zoomed in with the Watson camera, we also saw some of that purplish reddish splotchiness as well. So again, generating lots of good discussion about the presence of coating and alteration rinds that may be present on the rock and what this might look like. And this is a little different than rocks that we've seen in Gale Crater with Curiosity. So I think folks were excited to think about, what might be different between this landing site and Curiosity, where we have similar quality data sets. Okay, so those are the rocks of the landing site and what we've looked at there. I want to talk a little bit about these delta remnant deposits. So of course we have the main Jezero delta over here to the west, but a little bit closer to our landing site, we've had the opportunity to image some of these deposits here circled in this area and also down here to the southwest. And the idea with these deposits is that they are remnants of a formerly more extensive delta deposit that may be this exact delta deposit or perhaps an older deposit. And so we were really excited to get our first images of these remnant deposits and start thinking about what depositional environments they represented and what their potential geologic and age relationship was to the main Western Delta, as well as the rocks of the crater floor. And so this next image will be off in this direction, indicated by this black triangle here of the Santa Cruz Delta remnant, which is the main remnant out here in this area. And so this is what it looks like. It's a big mound. And it looks like while there is potentially some outcrop there, and that's maybe this brighter, lighter toned rock here, and then we can just see that down here in the left. Hopefully you all can see my mouse. But much of the surface of this delta remnant is likely scree and loose rocks and dust. And so probably not the most appealing target for Perseverance, given our desire to sample and understand kind of in-situ bedrock and its context. But it was spectacular, I think, to see these delta remnants for the first time, and raised a lot of questions about, what is the age relationship between these deposits and the crater floor where we sit, and the kinds of rocks that we see in the foreground, which are these more massive dark tone, but mafic and potentially sedimentary rocks as well. But the delta remnant that I think really was revealing in terms of depositional environment and process was these southern delta remnants to the southwest, in particular the Kodiak remnant. So this is a little bit closer to the Western Delta, and that's a little more easily correlatable to what we have actually exposed in the Western Delta. And we got this fantastic set of images down. So this is an image taken with the Mastcam Z camera, and just beautiful exposure here within this delta remnant. And the next slide will zoom in on this area over here to the right, and this area here on the left part of the image, where we can see these beautifully dipping beds that we are interpreting as cliniforms in a Gilbert type delta, where you have the cliniforms here and the top set and bottom set beds above and below. And this is entirely consistent with our understanding and the presence of the Western Delta here. And really firms up our interpretation of this landform in Jezero as a delta. Anytime you look at these kind of fan-shaped features on Mars, there is always the question of, is this a delta? Is this an alluvial fan? And so I think with these observations, we've really helped to convince ourselves that we are in fact seeing deposition into a standing body of water, and in a situation analogous to Gilbert deltas here on Earth. Okay, and then we've also had the opportunity to look at the delta itself, and this was one of our, I think, most exciting images we got early on, which was a SuperCam remote micro imager image off to the front of the delta, where we saw this deposit here in the upper part of this front delta scarp. And so I'll zoom in on different parts of this in the next slide, and so these boxes are what you'll see next. But zooming in, we have these beautiful boulder-rich lenses present here, as well as some bodies that had finer layering and dipping layering. So we've been thinking about the implications of these deposits for the depositional environment preserved within that main delta deposit, and coming to terms with the fact that these deposits seem to point to pretty high energy flows. And actually our ability to resolve these boulders at this distance was, I think, a really pleasant surprise, and a really nice use of SuperCam's focusable telescopic imager. And so this has been, I think, one of the most exciting images for us to pore over, those of us interested in sedimentology on the mission, thinking about what these big clasts and boulders might mean with respect to depositional environment here within the delta. And so I'm wrapping up here, but wanted to tell you a little bit about what is coming up for the mission. So here, just to localize you again, Octavia E. Butler Landing, we have since progressed a little bit further along this yellow path, but the team made the decision over the next about probably 3 to 6 months to devote time to exploring these crater floor units in great detail. So the crater floor rocks that you've already seen a preview of, as well as the rocks in this area just to the west of the rover, this kind of mitten-shaped outcrop that we've been calling Sita, which in Navajo means amongst the sand or sandy. And so right now we are planning a campaign to go around the tip of the thumb, as we've been calling it, of this mitten, to explore the crater floor rocks and understand the relationship between these two units, with the potential for exploration into this Sita outcrop. And so we expect that our first samples that Perseverance collects will come from this crater floor unit, as well as the rocks exposed within the Sita outcrop. And so this next slide shows you, I think, something that was most surprising to me, at least from orbiter images. Sometimes we see beautifully layered rocks, and you can even see this at this scale of the delta. You can see these layered rocks here, of course, being entirely consistent with a sedimentary origin within a deltaic setting. But here with the rocks exposed within Sita, it was less obvious that there was sedimentary layering or layering of any kind present within this particular unit. But when we got the first images down from this location, we saw rock outcrop like this, so beautifully layered, relatively thin planar bedding, with apparent variations in thickness between thick and thin beds, and some interesting textures that may be not nodular textures. And so this was a unit that didn't give us a whole lot of clues in terms of its depositional origin from orbit, but now that we're seeing it on the ground, the gears are turning to try to determine, what is this unit? Is it a sedimentary sublacustrine deposit? Is it potentially a volcanic ash? And we're considering other interpretations as well. So these are the kinds of rocks that we are excited to explore with Perseverance over the next couple of months, and we anticipate that some of our first samples will be from these units, and are excited to carry out this campaign. And then once we're done with that, we will head back on the road. At this point, our plan is to go north around the Sita outcrop and head to the delta front, where we'll engage in detailed exploration of the delta front deposits and some of our prime astrobiology targets there, and the kind of distal pro-delta deposits that we expect to find there. So with that, Ben, I'll hand it back to you, and hopefully left a little bit of time for questions, and happy to take any of those.
Yeah, Katie, thank you very much. So for everybody listening out there, we're getting in questions through the Q&A chat function. That's great. Keep them coming. Also, feel free to click the raised hands button, and we'll try to get to some of you who raised your hand. We should be able to unmute you if you'd like to ask a question directly. But Katie, let me take the first question, I guess. What's the timeline here for getting to the delta itself?
Yes, that's a good question, and one that we're always a little bit hesitant to answer, because rover missions on Mars are known for encountering lots of challenges, and so it's always hard to commit to a time frame. But we actually are doing our best this time around with this mission to keep to a very strict timeline, because we have this desire to put together a diverse cache of samples that requires us to cover ground and to see these different rock deposits that we know are present in and around the landing site. And so based on our best estimates, we are at this time expecting and hoping to reach the front of the delta by about our 1 Earth year anniversary on the surface of Mars. We are still in the process of getting some of our capabilities that will enable more efficient driving, still getting some of those online. And so once that's there in place, we expect to be able to make pretty good time. I'm not sure, I think I'm still sharing my screen here, but we expect to be able to make pretty good time around this northern tip of the Seta outcrop. It's pretty smooth terrain here, and we think we can make good progress. So the hope is to spend most of our time on the science part of it, exploring these rocks, and then we'll make a pretty rapid traverse over to the front of the delta. So our expectation is about an Earth year.
Great, thank you. Okay, so this is a question from Chuck Hell, who submitted this as he registered. Is there any evidence of surficial or subglacial subice sheet features seen in the basement, like maybe some sort of glacial scour?
That's a great question, and actually one that the team has been discussing very recently. I think there's some very interesting geomorphology here, even at the orbital scale, to think about in the presence of these remnant deposits we have, and the unusual and interesting shapes of outcrops like Seta, which I'm showing here on the screen, as well as thinking about, we've got these pretty consistent lineations. What does that mean? And then of course on Mars, while we don't have ice present here at the surface or near subsurface today, our understanding is that, of course, parts of Mars could have been covered with ice in the past, and that's certainly a possibility. And so I think that that's something we're open to exploring. I think we have some folks on the team who have pointed to some of the landforms in this area and thought, oh, could this have been formed in a glacial setting by glacial processes? And so we will be thinking about whether there are ways to test that on the ground with rover observations. If some of these landforms that we see were deposited by retreating glaciers or deposited in an ice-covered lake, what would that look like, and what might we expect to find with the rover? Thus far, I don't think we have found anything that conclusively points to action of glaciers here based on what we can see, but that's very much a hot topic that the team is talking about, and something that we're going to want to keep our eyes out for as we move along. I mean, anytime you have a surface littered with boulders, it's something you think about, but nothing quite yet that points uniquely or conclusively to the presence of glaciers here and influence yet.
All right, thanks, Katie. Chris Hells, I'm going to unmute you if I can, and please feel free to ask your question. Oh, can I unmute him? There you go, Chris.
Okay, what a wonderful presentation. Fascinating to see, fascinating to listen to. Thank you very much indeed for that, and thank you for everybody for organising this. The question I have is in relation to the differential gravity and fluid dynamic processes on somewhere like Mars and other planets. How much do you think that influences a direct analogy to processes that we would attribute to sedimentary features here on Earth, for example? I'm thinking particularly back to those lenses you described from the Delta, which were coarse-grained deposits, and you referred to them as high-energy deposits. I don't doubt they're high energy, but do you think that gravity and fluid dynamics on Mars would have been different in such a way that it's not quite the same interpretation we'd naturally have as process-based sedimentologist?
Yes, thank you for that question, and that's a really great question, because sometimes people tend to approach Mars, I think, in two different ways. One, you either think of it as an alien planet where everything is very different than what we have on Earth, or everything is exactly the way we have it on Earth, and we sometimes forget that things are indeed different and on the surface of Mars. And so I think with respect to the boulder beds and just kind of sedimentary processes in general, I think the difference in gravity is always something important to keep in mind. And folks have done the calculations to take, for example, the bed form stability diagram, and it shifts on Mars as expected, because the gravity is different, and that, you know, changes things in that kind of bed form stability space. And so that is something, and anytime one is doing calculations involving you know, things like how fast are the rocks moving, or is the water moving, or what is capable of being transported, you have to think about gravity and what role that might play. So that is something we think about and we take into account. And so yeah, it's a good point. I think at this point we're still working through exactly, you know, what kind of flows and what the energy of that flow would be. And so that's something we're still working through. But yes, we do always think about the role of that difference in gravity and what impact that will play as we are interpreting the kind of depositional settings that we see.
All right. So there's a question in chat from Kathleen. She's wondering about the rounded rocks near the landing site. Could they be concretions weathering proudly rather than transported clasts?
Yes, great question. So I think most of the rocks that we see kind of as the loose rocks present on the surface, the big ones, we think are basically broken up not too far away from in situ bedrock, and over the course of billions of years, you know, degradation of the surface, deflation, resulting in the accumulation of these boulders, and as well as the influence and role of impact cratering here. It's a very heavily cratered surface. So in terms of the bigger rocks, we don't necessarily think that those are individual concretions. But I think, for example, we've seen in Gale Crater with the Curiosity rover abundant diagenetic textures, and most of them tend to be smaller, so kind of millimeter size concretions are just, in some places in Gale, the rock outcrops are just, you know, chock full of concretions. And folks may be familiar as well with the blueberries that Opportunity studied, the hematite bearing blueberries. And so we certainly expect to see diagenetic textures like concretions, but in terms of the big blocks, we think that those are probably just broken up bedrock. But we certainly have our eyes peeled to look at the diagenetic textures here at this site, and to do comparisons between the kinds of textures that we might find here and the diagenetic features that we've seen at previous Mars rover landing sites.
Okay, Ishmael is wondering where the coring machine is on Perseverance.
Oh, yes. Okay, let me slide back here to the picture of the rover. And so the corer is on the turret. So let me see, I'm not sure that we can actually see. It might be right here, up here at the top. It's kind of hard to see in this image, but yes, the corer is here on the turret, and we have actually 3 different bit options for our drill. We have a coring bit and a braiding bit, and then a regolith bit that we can put on there to collect regolith samples. And so we have a bit carousel located over here in the body of the rover, where we can change out and swap those bits. And that's kind of an exciting engineering feat, because Curiosity has been operating with the same drill bit for the entire almost nine years of the mission. And so, but with Perseverance, we expect to be changing out those bits almost every time we do an action, whether it's abrading the surface or collecting a new sample. And then within the body of the rover is the kind of sample handling assembly and the whole sample caching system. And so inside, and I should have included a picture, but there's basically a whole series of stations. Once the sample is transferred inside the body of the rover that it will go through, as it is imaged, there's a volume assessment, and then it gets sealed into a tube that's then kept within the body of the rover. And when the time comes, we have the ability to drop those samples under the body of the rover and drop them onto the surface, with the idea that the follow-on mission and that fetch rover that I mentioned will come along to pick those samples up.
So what about the extra tubes that the rover is carrying? Norman noted that the plan is to take 30 samples, but there are some extras. Is that just some redundancy, or?
Yes, great question. So I think it's 5 or 6, and I'm forgetting exactly whether it's 5 or 6, but 5 or 6 of the tubes are actually witness blank tubes. And so they are tubes that have some material inside of them that can basically, we can puncture those witness tubes and use them as kind of a control collection device to understand what the state of the sample caching system is at any given time in the mission. So that's one of the reasons we have those kinds of tubes, is to understand potential contamination that might exist within the rover, and that rock samples or soil samples that we collect might have. And so the idea being that throughout the course of the mission, as we are doing our sample collection, we can choose to use one of these witness tubes, and then that tube will be opened and then sealed, and then we'll have a good representative of the potential contamination that might be present at the time. So when we go and look at those rock samples when they come back to Earth, if we see something unusual, we can go back to that witness tube and say, okay, are we seeing that also in the witness tube, such that the thing that we are seeing might actually have been some internal contamination from the rover, as opposed to something inherent to the Martian surface or Martian rocks. And so 5 or 6 of the tubes are used for that purpose. And then we do carry a number of other tubes that we kind of think of as the engineering tubes, with the expectation that there will be times when coring may not go as expected or be successful. And so building in a little bit of engineering margin there, in case coring doesn't go quite as expected every time. So generally speaking, we say that we plan to collect about 30 science samples, and then on top of that, we have the witness tubes as well as those engineering tubes that we may indeed be able to use for science samples, but we kind of we bookkeep them a little bit separately, given the need to hold some for engineering margin.
Yeah, it's pretty clever. So we've had a few questions here, sort of broadly asking about the shift from this, fluvial delta setting to the modern environment, which is, largely net erosional, driven by winds. How has that affected sort of the morphology in the crater? And in a broader sense, what may have caused that shift from this crater being, deltaic, fluvial, to being wind eroded?
Yeah, that's a great question, and it's actually one I'm thinking a lot about right now, with my curiosity hat on, in a research project I'm working on in Gale Crater. But it's a really interesting question, and one that's really key to understanding Mars and its evolution from habitable planet to uninhabitable planet. We have this fantastic geomorphological evidence that Mars was once host to ancient crater lakes, and we have deltas, and we have valley networks and possibly even, you know, a northern ocean or at least very large seas present in certain parts of Mars. But then again, obviously today, all of that water is gone. And so there are a couple of, I think, major changes that Mars underwent in its history, all kind of concentrated again around this like 3.8 to 3.5 billion year time frame when we transitioned from the Noachian period to the Hesperian period, that played a role here. I mean, one thing is that at some point around this time, Mars, it seems clear that Mars lost its atmosphere. And that may have been related to the fact that it lost its magnetic field. So Mars's ability to hold on to that atmosphere was decreased significantly. And then over time, it was simply blown away by things like solar wind and that type of thing. So with the loss of Mars's atmosphere, then I think that really put the ability for liquid water to be stable on the Martian surface, you know, it really changed the situation there. And so at the same time, or shortly thereafter, we have the formation of some of these major volcanic centers on Mars. I mean, the biggest volcano in the solar system, Olympus Mons, is here on Mars. And so there were some pretty major things happening where we transitioned from a period of time on Mars where liquid water was stable on the surface. We had the formation of these landforms that suggest sustained bodies of water over time, to then a period of time where that water is gone, the atmosphere is gone, and then we move into a volcanism is dominating on the surface of Mars period. So that was a pretty intense major shift here. And then once those volcanic centers and volcanic activity died down on Mars, we go into, you know, at least several billion years of aeolian abrasion being one of the dominant processes affecting the landscape of Mars, and really being the dominant process here, coupled with impacts as well. And so anytime we look at a place on the surface of Mars, and particularly a place like Jezero, which has very interesting and complex morphology and interesting landforms to look at, and even just the kind of erosional nature of this contact between where we've landed and then these rocks in Seta, you start to think about, well, what did this environment, what was the history here that led us to this current landscape? And sometimes I think of the surface of Mars as frozen in time, but then you think, you know, this entire crater could have at one point been completely filled with sediment, and that's now just gone and completely excavated. So we also have on top of this cycle of erosion and deposition that we, I think, are really only able to probe in detail with, as we get rovers on the surface and understand and are able to recognize unconformities and major unconformities within the rocks that we look at. And of course, some of that can be done at the orbital scale as well, but I think there are details there that we are now appreciating now that we've got rovers on the surface. So I think this is just a long way to say that there's been some pretty major changes on the surface of Mars from the time when we think ancient crater Lake Jezero was present to today. And one of our jobs is to disentangle and figure out whether what we see on the surface was something that, is it there because of how the original depositional conditions were, or are we seeing some subsequent modification by ice, by wind, and what might have caused the landscape to look the way it does today. So it's this big puzzle that we seek to put together and figure out. But these kinds of questions are very relevant to us, and particularly given Jezero and its complexity, things that we are very actively thinking about today, and thinking about, well, you know, is the outcrop shaped like this because there was a former deposit here that has since eroded away? And is that why we see this interesting shape? And so those are the kinds of things that we're constantly asking ourselves. And even just, you know, how extensive was the Jezero Delta? Obviously, we're missing parts of it. So what did that used to look like in the past? So I think it's this combination of what are the rocks telling us and what is the modern landscape telling us, and our attempts to put those things together.
I think that defines maybe the state of Mars sedimentology across the whole planet even right now. Yes,
I think so.
Katie, I think, I see Howard here has a question. Howard, I was actually just about to read yours, but let me ask you. or let me unmute you and let you read it.
There. Thanks. So really interesting again. And so I've been zooming in on some of the parts of the crater, and I had a couple questions. One is how thick are those cliniforms? I'm surprised you didn't have a rock hammer there or something for scale. And but they look really interesting, and they look just like Gilbert deltas. And then about the erosion on the edge of the resistive beds, you know, in places where you look at that, it looks like there are blocks that have fallen down. If I was out west, I'd say those are blocks of sand that have fallen down over a more erosional sand shale bed beneath it. It sure looks like the kind of erosion you see out west today that was all caused by water.
Yeah, so I'll answer your first question. The cliniforms are on the order of a couple of meters tall, less than 10. And I think maybe somewhere closer to about 3 to 7. And in terms of your comment here, and I think it's in reference to this area where the rover landed. So yes, we do have, I mean, I think all signs are pointing to the fact that the rock unit and the surface that the rover landed on is more resistant to erosion and harder than for example, the rocks to the west. For one, it's a more heavily cratered surface. It retains craters better. So that suggests to us that it is more resistant to erosion. And then of course we see this scarp here and the shedding of these blocks down into this area that's been more easily eroded and excavated out.
Yeah.
But I think whether or not.
Yeah, sorry, I was referring to the terminal end of the delta a little bit further to the left there, where there's some, so you can't really see the blocks at this scale, but if you zoom in to the edge of the delta, there are places where it looks like I'm just going to call them sand beds that are holding up the face. There's places where there's blocks that are a few meters, just barely at resolution, that have fallen down. And so it looks like the kind of erosion of the more easily erodible beds that sure look like shale, and the sand beds have fallen down, which suggests to me water erosion has eroded some of those beds. And some of the beds look like they're jointed. So you see joint faces on the blocks that have fallen down.
Yeah, those are great observations. I think one of the things we always have to think about for a place like Mars is, again, the role of billions of years of aeolian abrasion and the backstepping of the landscape, perhaps due to wind. So I think that's always something we think about and think about, okay, is there also a possibility that we could have shaped and formed this particular landscape through the action of water? So I think that's definitely something we're open to. But I think simply the time dominance of aeolian processes over in the most recent time on Mars always gives us pause, I think, when we're thinking about, okay, water or wind as the dominant erosive process here. And so that's very, very, very relevant to think about, and something that I think we're actively working on and haven't necessarily come to a conclusion of what resulted in the erosion of the delta to its current form, and what different processes might have been involved in that shaping of the landscape.
Katie, just a couple more short ones for you, I think, and we'll let you go. First is from Tim Gouge, who's curious about the interpretation of the meter scale cliniforms as far as a delta front or a point bar lateral accretion surface. And the second would be Ajay, who's wondering if there are any more hypotheses about the large clasts observed in the Mastcam images.
Yeah, so I'll address maybe Tim's question first. Yeah, we certainly did think about the possibility of some kind of migrating bar form here. Sanjeev Gupta and Nicola Mangold are currently working up a paper, and likely to be one of the first papers of the mission, describing these outcrops and what our interpretation is. And I think the prevailing thought at this point is that they are are not consistent with bar forms, and that they are more likely to be delta cliniforms. And I don't necessarily have the images to zoom in here, but some of that had to do with some observations we made about clasts and cobbles within some of these foresets and dipping beds, and kind of relative changes in thickness and thinness, and comparing to some examples of bar forms here on Earth and what we might expect to find if that was the interpretation. But I think the team is very much moving towards consensus opinion that interpretation as delta cliniforms is the favored interpretation here. But we did think about the potential for bar deposits, but that was decided not to be the most favorable interpretation. And then also the context here, I think, plays into that as well, with the presence of these beds above and below, and I think things kind of falling into place that what we may be seeing is the top set, bottom set, and then the four sets in between. And then Ajay's question about the boulders. Yeah, so we thought about what, well, in terms of interpretation of what those represent, I think given the setting and given the shape of the deposits as these kind of lenses, bouldery lenses, with better bedded laminated rocks here, some cross-bedded sandstones here, very much thinking that we are in a kind of fluvial setting, subaqueous fluvial setting. I'm not sure, Ajay, were you thinking, I don't know if you can unmute, were you thinking of things like debris flows, that type of thing as alternative hypotheses?
Yeah, I was mostly curious about just what looks like this huge, how you get such a big contrast from what looks like much finer grained material. What kind of hypotheses are in the room right now as you discuss these great images?
Oh yes, yeah. So that was, I think, something. Yeah, we have talked a little bit about that and what would create that differential. And so I'll just throw out one example of an idea that was thrown around. Something like, did we have an ice dam further up in the system here, that when that gave way or released, we then had this high energy flow come in with the ability to transport these big boulders. And so we've explored kind of the sort of more catastrophic ideas here for deposition. And so that'll be coming out in that first paper. But that's an example of the kind of thing that we were thinking about there, and whether there was a reason to invoke kind of more catastrophic events to help explain some of the differences we see in energy and kind of grain size here within this particular outcrop.
All right, Katie, thank you so much for sharing these great updates with Perseverance. We really appreciate it.
Yeah, thanks again for the invitation, and to those who called in to listen in. Thanks a lot.
Yeah, thanks to everybody here for showing up and interacting. We'll send out some information regarding the polls, so keep your eyes peeled for that. Your email is open, and I think that concludes our first research group meeting, the Planetary Research Group. So okay, thanks everyone. Thanks to Cassie and Rebecca for helping in the back end here. And yeah, have a good day. Take care.